Lecture 79. This lecture is on solids, so we're going to transition into talking about, well, solids, liquids, and gases, and how we treat them in physics. We'll also put some thermodynamics in here as well, so it'll be kind of our first contact with thermodynamics. But today we're going to talk about solids. But just keep in mind that solid and liquid, right? You know the formal definitions of these things, right? Solids, they retain their shape, right? Liquids, they maintain the shape of the container in which they're, well, contained. And gases, they tend to diffuse in every direction, right? So they're hard to contain. You can only contain them in an enclosed volume. And they will fill that uniformly, okay? But, you know, what's the difference between, say, a solid and a liquid? Well, think about glass, right? Glass is kind of like a liquid. It's always kind of flowing, right? If we were to like have some glass windows and, you know, wait a few hundred years, you'd see the windows would kind of pile up at the glass would pile up towards the bottom because it's always flowing. It's in a flowing state. If you think of the rocks in the Earth's, you know, mantle, where it's down where it's very hot and high pressure, right? These rocks behave like liquid over time. You know, granite, for example, which is what the continents sit on, they are buoyant in, you know, the rock substrate in which they sit. They have a lower density, and so they're kind of buoyed up in comparison to, I forget, what is the ocean floor is made of? It slips my mind. I'm not a geologist, so. But anyways, so there's kind of it can be tricky, the boundary between these things, right? I mean, but, you know, in general, if we, you know, stick to these rigid definitions, we can think, right, that if we start out with, say, a solid, maybe this is a piece of ice, right, and we add heat, and we haven't formally defined heat, but you know what I mean, right, when I say add heat. What you'll find is that this will kind of melt into a puddle, right? If we continue to apply heat, right, so we've gone from solid to liquid, and add even more heat, right, and now we kind of have a gas. Everything is, the puddle is very small now, right? Everything evaporates away, is flying in every direction, right? Yes? Yeah. Now the interesting thing to note, right, is that what happens after the phase change starts to take place. So you start to add heat to something, and at some point it begins to melt. Now, the interesting thing is the temperature of the body will stop changing at that point. At first, when you start applying heat, it'll warm up, okay? And once it reaches the transition temperature, it'll stay at that temperature until the phase transition is complete, you see? And then it'll start gaining temperature again. The temperature will start rising again once it's in the liquid phase, right? So if this was ice, you know, this could have started out at, say, 30 degrees Fahrenheit. What is the freezing in Fahrenheit? I never get that right. Let's say it's -4 Celsius, okay? So that's below the freezing temperature for water. You heat it up until you get to 0 Celsius, then it begins to melt. It stays at 0 Celsius as you dump heat into it. Turns into liquid, and now the liquid, which is at 0 degrees Celsius, starts to rise. Right? It'll go up until it gets to 100 Celsius. And then it'll stay at 100 Celsius as the puddle evaporates away and it turns into a gas. And then the gas, if you continue to apply heat with it into it, you can heat up the gas as well. Okay? So that's kind of the idea of heat regarding the phase changes of these things. But we're going to focus on solids, and so we have to begin with some just general metrics for solids. Here are a few different shaped solids, right? Solids have shapes, right? Now they can have any shape, but you know, some common ones are, you know, cube-like shapes, sphere-like shapes, and cylinder-like shapes. Okay, and as we work with these with this stuff today, we're going to need some like formulas for this. We're going to need things like volume. So what's the volume of a cube? Anybody? If this is the length and this is the width and this is the height, what is the volume formula for a cube? Or what do they call it? I don't remember what they call a rectangle version for the three-dimensional rectangle. Rhomboid? I don't remember. But anyways, who knows the volume formula for this? Nobody?
H times L times W?
Yeah, of course. It's exactly just the product of these three dimensions, right? It's the length times the height times the width, right? If it really was a cube and all three were the same length, right, you'd say it was L cubed, right? But look at the face of the cube. The face of the cube is an area, right? And so if we were to slice this cube, and we'll do this, it's called a cross section, right? If you cut the cube such that you have a face that looks like that or two of them when you finish cutting, right, its cross section is this square cross section, or rectangular cross section, right? And so the cross sectional area, I'll put CR for cross-section, in this case is equal to, well, I guess it'd be the height times the length in that case, right? What about this one? This is a sphere. What's the volume of a sphere? Anybody?
The radius times pi squared.
That's the area. So it turns out the volume for a cube is 4/3 pi r cubed. Okay? It's a trivial thing to do if you have calculus, you can integrate, but if you don't, then I think maybe it's best just to memorize. I have to think about that, whether there's a non-calculus based way to do it. There probably is. If I were to slice it though, right down the center, right? I have to slice through the center point of the sphere. If I do that, then we'll get a cross-sectional area, which is equal to pi r squared, right? Yeah. If I don't slice through the center, then the radius will be less, right? You can imagine slicing it right at the edge, right? It's going to be, a much smaller radius. So if you imagine something going out and dropping down like this, right? This distance here would be the radius of the cross section, right? What about the cylinder, right? Cylinder, I think it is easiest to start with the area, the cross-sectional area. If I slice a piece off of a cylinder, right, like this, then I get a circle as my cross-sectional area, right? So that's pi r squared. And if I imagine, this is how you get volume formulas in general, creating a really large number of slices and then adding them all up, right? Make them infinitely thin, but have an infinite number of them, right? And if you add them all up, you're going to add them from 0 to L, right? Then this is just going to give you the volume formula for this. It's pi r squared times L, right?
Yeah.
So volume formulas are useful for doing what I'm about to show you next, which is one of the basic, measurements basic characteristics of a solid, right? Perhaps the most basic characteristic of a solid, in a general sense, is its density, right? How much mass does it have per unit volume? Okay? So usually we use rho for density, okay? And it's just equal to the mass divided by the volume, okay? Not too tricky, right? I think I have some numbers, examples. So for example, even though this isn't a solid, but rho of water, just for comparison, is a gram per cubic centimeter. But SI units, this would be 1,000 kilograms per cubic meter. So yeah, a cubic centimeter is a good reference for thinking about masses, right? And so to think about what 1 gram is in terms of its size, right? And remember, a centimeter is about the size of the width of your pinky nail. So that should give you some idea how big this little cube would be. But 1,000 kilograms per meter cubed, that's water. So what about something like lead? Lead is really, really dense. So the density of lead is 11,300 kilograms per meter cubed. So what would that be? What would that be in grams per cubic centimeter? It'd be 11.3 grams per cubic centimeter. Just the way the units work out. I'll leave that as an exercise for you guys to practice converting between various volumetric units. It's not as trivial as you might think. It can surprise you a little bit. But anyways, another metal, aluminum, has got a density of 2,700 kilograms per meter cubed. And iron, which is very close to steel, is 7.96. I think this should be grams per centimeter cubed. I think I wrote the number down wrong. So 7,960 kilograms per cubic meter. Okay? So let's see how we would apply a problem to this, right? So let's pick one of the lead, okay? We'll keep the value of lead up here. And let's ask the question, how big would a lead brick be if it had the following dimensions? We'll go 10, 5, and 5. Okay? So it's 10 long, 10 centimeters, let's say. 10 centimeters long, 5 centimeters wide, and 5 centimeters high. And so the question is, how much does this brick weigh? Okay? So how would we figure that out? Well, we would use the density formula, right? Since density is equal to mass divided by volume, and we want to know what the mass is, right? We're going to solve for mass, and we'll write it as density times volume. pretty straightforward, right?
Yeah.
And so we can plug this in. This will be 11.3. I'll use grams per centimeter cubed here because these are in centimeters, right? So then I've got 10 times 5 times 5 centimeters cubed, right? So this is roughly 11, right? This is roughly 250. Well, no, it is exactly 250. So it's 250 times 11. Everyone remember the rule for multiplying by 11? Just call this 11, and we'll call this 250, right? You can see that the centimeters cubed are going to cancel out, and I'll be given an answer in grams. Who can do 250 times 11? Anyone remember the trick? It's pretty easy, actually. All right, so 2. 5 plus 2 is 7. 5 plus 0 is 5. And then the last digit, 2,750 is 11 times 250 grams. So 2,750 grams is the mass of that brick. Okay?
All right.
Stress and strain. Okay? This is kind of the meat of the course, or of the lesson. Okay? So first, let me just say this: if we look at solid, you know that things are made of atoms, right? Yeah. And if you look at what the potential energy surface looks like between a pair of atoms that are bonded to each other, like they might be in, say, a solid, okay? The potential energy surface looks something like this. Here's U, here is R. That's the kind of the interatomic or intermolecular separation distance, right? So the distance between the atoms or molecules that make up the solid, okay? That's what R is here. And it's going to look like this. It's going to be very steep coming down like this, and then it's going to kind of trail off like so and asymptotically approach this value here, okay? The equilibrium position will be, you remember when we talked about potential energy surfaces, we said just imagine that it's like it's a ditch or a ditch. There's another word that I'd like to use instead of ditch, but I can't think of what it is. But a well, maybe, right? It's in this well, and it's going to roll around until it reaches its equilibrium position here at the bottom, right?
Yeah.
Yeah? So that's its equilibrium position there. And, empirically, right, this comes into play through what's called the Lenard-Jones potential. You don't need to really worry about that too much, but it's something of the form of like A over r to the 12th minus B over r to the 6th. This is this part of the curve here. The r to the 6th is this part of the curve here. Okay, and it's empirically fit for a particular material. Okay, so they do some measurements in the lab. They determine what the values of these coefficients are, and now they have some model they can use to calculate, simulate, whatever, something about this solid or liquid or gas. Okay. Yeah, so this is kind of the repulsion, repel, attract, I guess you could say. So let's look what happens when we try to pull these two atoms apart, right? Well, so if I pull on the material, right? If we just think of the atom and I pull on it, right? This is the potential that's pulling back, right? You can see that it starts off kind of linear at first, and then it's going to start leveling off a bit here, right?
Yeah.
But how do we think about that in terms of, we can't pull on individual atoms. We can pull on, say, a rod of material. So what if we had a rod of material like this? And let's consider just a section of it here, right? A little section of length L here, okay? And I'm going to apply a force. One on this end, one on this end. These are called tensile forces. They're in opposite direction, okay? The tensile stress is defined as delta F over A, where A is the cross-sectional area. I forgot to make the A. So if we think of this cross-sectional area, right, there's R, it's kind of a circular cross-section, right? In this case, for the rod.
Yeah.
So it's the applied force that the force that you apply divided by the cross-sectional area. Now the strain, so we'll call it tensile strain, is defined as delta L over L. Okay? So if I introduce a change in the force that I apply, right? So I'm applying a force that's at length L. Now I apply a little more force. It changes its length a little bit because it's stretching, right?
Yeah.
And so the definition of the strain, right? That's kind of the material's response to the stress that I've applied, is given by this formula here. So the change in the length of this little section here divided by the length of that section. Okay? Does that make sense?
Yes.
Yeah? So if we were to look at, we need one more definition here. And we can kind of put these two things together in something called Young's modulus. It's an uppercase Y for Young, okay? And it's just the stress divided by the strain. Okay? And that is, and this will have units of newtons per meter squared. It turns out to be the same units as you'd get for pressure, right? Which is the force applied on some area. I want to draw a curve to see what's going on here, okay? Just to show you for general solid materials. So I'm going to make this axis the stress axis, and this axis the strain axis, okay? And so as we increase the stress, it will stay linear for a while, okay, up to a point. At some point, and this we'll call like the Hookean region. This is where Hooke's law applies. Do you remember Hooke's law? Hooke's law. F is equal to minus kx, right? That the force is oppositely directed, the displacement, or I guess you could call that delta x if you wanted to. If I create a delta x, it's going to have a force. This is called the spring constant, okay? The springs involve more than just the tensile stress and strain, okay? But the same idea though, okay? Hooke's law applies to just steel rods as well. You wouldn't think metals are elastic, but they are. And so we also call this elastic behavior, okay? When you can pull on it, and if you release it, it'll return to its original shape, return to its original length, okay? That's elastic behavior. But at some point, right, this starts to tail off, right? If we try to tie it back into the Lenard-Jones potential here, right, you can see that it's linear for a while, but then the slope starts to change on this potential energy surface. And so you end up getting a slightly different kind of behavior here, okay? And finally, we can call this point here the elastic limit, okay? And after that, any further displacements that you make, right, will not return back to their original length, okay? And so we call this the fracture point. That's where it breaks, okay? So I start pulling on, a steel rod. The stress will increase linearly with the strain will increase linearly with the stress. I always get the two confused. Which one is the force term, right? So you have to look, well, stress, that's the one that has the force applied. Okay, so you apply a stress, and the material has a strain, right? So it's kind of its response. So the strain will be linearly proportional to the stress up to this point here, right, where now it's behaving nonlinear, but it's still elastic, okay?
Okay.
And then we reach the elastic limit, and at any further stress beyond this point, the material cannot recover and go back to its original length or shape or whatever, okay?
Okay.
So that's just a general characteristic of it. Yeah, and the tensile stress is specifically just to pulling like this. There are a couple others, right? I'll just mention them casually here. One is called the shear stress. And I have to draw a picture for you to see what that looks like. It's where I apply a force in this direction and a force in this direction, but on the bottom, you see? So I'm pulling at the top of this here, but I'm pulling from the bottom here, right? It's a shearing force. Do you understand?
Yes.
The difference between this shearing force and this tensile force? Yeah, tensile stress, right? So this is a shear stress. It's causing the solid to deform like this, you see? So it started out in the solidly colored lines, and it ended up the dotted colored lines. That's where it ended up. And so this would be some little delta x that you get, right? This distance here, right? And we could call the length L of the section. But the shear stress would still be just this delta F, this time it's shear over the area, right? But the shear strain would be delta X over L. Where actually L is going the wrong way. This should be L here. Kind of think of it as like the distance that separates these two shearing forces. Okay? If L was 0, you've got yourself a tensile stress. Okay?
Okay.
If it's not 0, then we have a shear stress. Make sense?
Yeah.
And there's another one. It's called the bulk stress and the bulk strain, and that has to do with you might take an object with a known volume and submerge it in water, so that as it goes deeper in the water, the pressure increases. So it's pushing from all directions, okay? And so it's very similar. The bulk modulus is similar to the Young's modulus, except there's a negative sign, because when you push in on things, it always gets smaller, right? But I'm not going to worry about that too much. But let's do a quick example on how to use this stuff in like a problem. So I'll put it over here, I think. Got some room here. So let's imagine that we have a little steel cable. The cross-sectional area on this, I'll call it A cross, is 0.1 centimeters squared, okay? And I'm going to suspend a load, it doesn't really matter what the shape of the load is, but just draw it like this, of 1,000 kilograms from this cable. And how long do I want the cable to be? I guess I want it to be, I don't know, a meter long, okay?
Okay.
You understand what's going on here? Yeah?
Yeah.
So I want to figure out how much is that steel cable going to stretch, right?
Yes.
When I put this 1,000 kilogram load on it. All right, let's convert this area into meters squared, since it's an area, just for convenience, and you'll get to see how to do these kind of conversions. So I want to take 0.1 centimeters squared times, I want to get something that's meters squared divided by centimeters squared, right? Well, how many centimeters are there in a meter? Well, there's 100, right?
Yes.
100 centimeters in 1 meter, but I don't need meters to centimeters, I need meters squared to centimeters squared. So we have to square this whole thing, right? So it's going to be 0.1 times 1 times 10 to the minus 2 squared would be minus 4, right? And 0.1 times 1 times 10 to the minus 4 gives us one more. It's going to be 1 times 10 to the minus 5, right? And that's meters squared. So just get it in SI units. So what is the force here, right? What's the mass? 1,000 kilograms times the acceleration due to gravity, 10 meters per second squared, right? So that's going to be 10,000 newtons, right? 10, which we'll write as 1 times 10 to the 4 newtons, okay? It's 10,000 newtons. That's the force. All right, I'm missing one very crucial piece of information, right? This is steel, okay? And I need the Young's modulus for that. Try to go down. Okay, so the Young's modulus for steel is 1 times 10 to the 11 newtons per meter squared. Okay?
All right.
I think that's right. Is that right? Oh, sorry. There's a 2. It's a 2 times 10. Not a huge difference, but that's fine. 2 times 10 to the 11th newtons per meter squared. So stress over strain, right, is Young's modulus, right? Stress over strain. And that's the stress. It's going to be the 1 times 10 to the 4 newtons divided by 1 times 10 to the minus 5 meters squared. And then this will be divided. What is this going to reduce to? Well, this is going to be divided by the strain, which is the delta L, we'll call it, over 1 meter. So divided by 1. Okay? So just need to fix this up. So we have 10 to the 4th times divided by 10 to the minus 5. What's that give us? That's 1 times 10 to the 9th, right? Newtons per meter squared over delta L. Let's now solve for delta L, right? So we'll say delta L is equal to this 1 times 10 to the 9 Newton per meter squared divided by Young's modulus, which is 2 times 10 to the 11th newtons per meter squared. The units are, of course, going to cancel because a change in length. Oh, this is really delta L over L, I guess. My bad. So it's the ratio of that, okay? Yeah, I said that L was 1, but I didn't put the units in. So, but anyway, we'll just do it like that. We'll have delta L over L is equal to 1 times 10 to the 9th divided by 2 times 10 to the 11th. It's going to be 1/2 times 10 to the minus 2. It says delta L over L, 5 times 10 to the minus 3. So if L was 1 meter, right, then 5 times 10 to the minus 3 meters is 5 millimeters. So 5 millimeters is the amount that this steel cable will stretch when we put a 1,000 kilogram load on it. Okay?
Okay.
And that's how you calculate that. All right? right, there's one last thing I want to talk about. So stress is one way to lengthen, say, a steel rod. Another way to do it is to add heat to it. Okay, so this is called thermal expansion. Okay, so thermal expansion is thermodynamics this time. Okay, whereas the stress and strain is purely mechanical, right?
Yeah.
Thermal expansion is thermodynamic in nature. So we're going to make reference to concepts we haven't even defined yet, like temperature and heat. We're going to talk about heat a little bit in this lecture, but temperature as well. Okay, and so we'll use the Kelvin scale, which has the same gradation as the Celsius scale. It's just you have to add 273, or I assume you have to subtract 273 from it to get it in Celsius. Okay. So what is the idea behind thermal expansion? Well, we'll come to learn that when you put heat into a solid, or into any matter, it causes the atoms and molecules to jiggle around. Okay. Now solids, the atoms and molecules must somehow be confined. Okay, and I don't know to what degree we'll talk about it, but the basic idea is that there's a structure there, they bond together, and they're kind of semi-rigid, right? They're not moving around like they are in, say, a liquid, right? That's where the molecules are all kind of, they're still bumping into each other a lot, but they're not stuck to each other, okay?
Okay.
When a solid, the molecules and the atoms, they're stuck to each other, and they're somewhat rigid, you could say, okay? But if you put heat into it, then what's going to happen, it's going to cause these atoms and molecules to jostle around, they're going to vibrate, okay, a little bit. Now, this potential that I wrote up here earlier, the Lenard-Jones potential, you'll notice it's very asymmetric, okay? So if I give it some more energy, right, by dumping heat in, let's say I bring the energy up to here, this level here. You can see it's going to oscillate back and forth. Remember how we talked about thinking about these potential energy surfaces as marbles rolling in these wells, right? Back and forth. Well, this is not a symmetrical well, okay? And so if I mark out this equilibrium point, you can see that the motion that it's going to move to the left of this equilibrium point is much smaller than the motion to the right of the equilibrium point, you see? And so when you put energy into a solid, it tends to make it get longer, okay? And there's nothing magical about this, it's very empirical. So as T goes up, delta L goes up, all right? And so we could write that delta T, the change in the temperature, times what we call the coefficient of thermal expansion, right, will be equal to delta L over L, okay?
All right.
So whatever the length was before, right, the ratio of the change in length to its original length is given by the change in temperature times this thermal expansion coefficient, okay? If you want to know how much expansion was going to take place, you just solve for delta L, right? And I'll just give you L times alpha times delta T. And you can figure that out. For example, for steel, so alpha for steel is about, what is it? 11 times 10 to the minus 6? 11 times 10 to the minus 6, 1 over kelvins. Kelvins is a unit of temperature, right? What else do I have? I wrote down steel and I wrote glass. And so for comparison, the thermal expansion of glass, that says steel. Alpha for glass is what? 9 times 10 to the minus 6. 9 times 10 to the minus 6, 1 over kelvins. And then maybe one more, aluminum. 24. 24 times 10 to the minus 6, 1 over kelvins. So which one of these is going to expand more when I heat it? Aluminum, glass, or steel?
Aluminum?
Well, the expansion is proportional to the thermal expansion coefficient, right? Or the coefficient of thermal expansion. And which one has the largest thermal coefficient of thermal expansion? It's aluminum, right? So aluminum will change the most when you heat it up. Interesting thing, and I'm not going to demonstrate it, but it's not hard to show. I think I'll leave it as an exercise, actually, to demonstrate that the kind of the delta V, right? How do we say that? The thermal expansion, the coefficient of thermal expansion for a volume, right? So it expands in every direction, right? Is approximately, for small temperature changes, anyways, it's 3 times the thermal expansion coefficient. Let me write it this way. I'll leave this as a homework assignment for you. The delta V, V naught delta T, is equal to 3 alpha. the thermal expansion coefficient. Okay?
Yeah.
So instead of just using, a factor of 1 alpha, you'd use 3 alpha for a volume change. And it's not that hard to show. I think that is all I wanted to say about solids. Next time we'll talk about liquids, which are fun because you get to talk about buoyancy and stuff, and then gases. And probably a couple of gas lectures because we need to do the thermodynamics in gases a little more involved. So there's more to say, so to speak. And there's plenty to say about solids, but solid state physics usually requires a little more background material than what we already have at our disposal. I mean, we have the idea of potential energy surfaces, so we can think about it to a degree, but the way that we explore solid state physics is using the interaction with radiation of various types, whether it be light or X-rays, things like that. And we haven't really talked about light yet, so can't go into too much detail on that. Scattering, essentially. Any questions that you have?
No.
No? Okay. Well, I think that's it.